Now, let's have fun with cardiac cycle. Now, you know, in the heartbeat initiated by SAN. SAN is sinoatrial node. It is a mass of cells. It is a mass of cells that are specialized to give current. Okay, to give current. So, like in the cells of an eel, electric eel. You know this electric eel? It gives, if you touch it, you get electrocuted. So it is the same type of cells which is found in the heart. It gives wave of electrical activity. So we call it wave of electrical activity. So the SAN, which is found here in the heart muscle, in the cardiac muscle, it gives a wave of electrical activity which spread over the atrial wall. So here you have the atrium, here, the top. It gives the wave of excitation through both atria. Okay. Now the wave of electrical activity moves through the atrial wall, causing both atria to contract simultaneously. So both atria will contract simultaneously because the wave move in the cardiac muscles in the atrial wall and causes them both to contract at the same time. There is non-conducting fiber between the atria and the ventricle wall. So between the atrial wall and the ventricle wall, here we have a non-conducting fiber. So what happens? The wave cannot pass directly to the ventricular wall. It is stopped by the non-conducting. So all the wave converges to the AVN. Here this is the AVN, atrioventricular node. Okay. So the waves passes down directly. The AVN picks up the excitation wave after a delay of 0.13 second approximately. 0.13 second. After a delay of 0.13 second, therefore, after the wave of excitation converges and direct into the AVN it moves down here to the apex, and there is a delay of 0.13 second. Because the cardiac cycle itself is 0.8 second. So 0.13 second, there is a delay between the atrial systole and the ventricular systole. Now, the wave of excitation passes down along the Purkinje tissue. This is the Purkinje tissue between the two ventricles, which run down the septum. Purkinje tissue is the nerve fibers which is found here. This is Purkinje tissue, the nerve fibers, right? This muscle is the septum between the ventricles down the apex of the heart. The wave is spread outwards and upward. This is what the examiners want. The wave is spread outwards and upwards. Outwards like that and upwards. So it moves like that. Okay. So causes the cardiac muscle to contract from the bottom up. From the bottom up. Okay, so the ventricle contract from the bottom up to squeeze blood upward into the arteries with great force. When we are talking about force, we talk about muscles. So the muscles are thick, so it gives more force to the blood when it moves into the arteries. So you have to know the SAN that give wave of electrical activity that moves through both atria and causes both to contract at the same time. Non-conducting fibers between the atria and ventricles, so the wave of excitation cannot move to the ventricle. but they all converge to the AVN. From the AVN, there is a delay of 0.13 seconds because during this time, the wave of excitation moved down the Purkinje tissue along the septum to the bottom of the heart, and from here it is spread. It is spread outwards. It is upwards and outwards, outwards and upwards through the ventricular walls. Causes the cardiac muscle to contract bottom up. This is very important. Bottom up. This is what gives its force. Okay, so this is the control of the heartbeat, the nervous control of the heartbeat, and this you should know by heart. By heart. Now let us continue with the cardiac cycle. Now, things that you should know on cardiac cycle. Later on, we are going to see the valves and the graph of the pressure. Let us see for the time being what happens in the heart during ventricular systole, atrial systole. Systoles mean the heart is contracting. The atria are contracting. Ventricular systole means the ventricles are contracting. And the ventricular diastole means, the ventricular diastole means the ventricular diastole means the ventricle are relaxing. Now, what happens here? You can see for some time both are relaxing. So blood from the vena cava and the pulmonary is here. This is the pulmonary vein, and this is the vena cava. This deoxygenated blood, and oxygenated blood get in the heart, so it fills both of them. It fills both of them. For example, there is 70 here, 70 centimeter cube here. Say for example, I give you example just to understand. And this is 30. After some time, the two valves are closed. These are not valves, these are sphincter muscles. Sphincter muscles. These are not valves. It is controlled by nerves. Okay, now it relaxes, then it moves here, through both. Okay, due to gravity, it gets down more. And this. Now, what happens here is the two sphincter muscles close, vena cava and pulmonary vein close. So now you have this starts contracting. Now this is atrial systole. This is contracting. Can you see this is contracting? The wall is contracting because we have some blood in it. When it contracts, there is 70 here. The 30 will move down. So it is emptied. Now it is full with blood. As soon as the blood moves down, the valve closes. The valve closes here. As soon as the valve closes here, the atrial, we call this atrioventricular valve close. This one open and this one open. So at the time the blood is moving up, blood is moving in it at the same time. So for example, after this is contracting, say for example, 30 has moved here. Now all the 100 has moved out. Okay, an example I'm giving you. So all the blood move out, it is moving, it is contracting from the bottom upward. These two arrows show that there is ventricular systole. Systole means contracting, and it moves up. So this now after this, what will happen when this is a lot of blood is getting inside here? This open, these two valves open, and this repeats. You get the point. As soon as the atrioventricular valve open, this close. This is the seminal valve. semilunar valve. As soon as the atrioventricular valve open, this close. Okay, and now when this close, these two close, this open and this continue to open, so the blood move down. So more blood move down. Okay, because don't forget that the atria are small chambers, and these are large chambers. So a lot of blood is pumped out. Okay, now, so you get the point. So here the cardiac output will be about 100 centimeter cube. This is an example, an exact science. Okay, so the cardiac output, no, not here, from here. Cardiac output is from here. Okay, now it is, and 100 is moving out, 100 is moving out here. So a revision, right? Now, blood is moving down. Say for example, 70-70, both are open, these two close, both are open, the sphincter muscle and the atrioventricular valve open. This is ventricular diastole, and both ventricular and atrial diastole. Open, blood moving down. Now, the time that the 70 move down, there is still 30 here. This close, these two close. Okay, this is still closing, these two close, this is still closing, this contract, atrial contract, the 30 which is left here move down. After this move down, the ventricle will start contracting. So before it contract, these will close and the two here will open. So you can see that there is a relation between the opening and closing with the quantity of blood found in the atrium. You can get the point here. Look at here. We have 30, so it opens. Look here. When it is empty, the blood is moving down. It is empty. When it is empty, the pressure is less. So you see it opens and then it closes. As soon as this closes, this opens. Okay, now let us see a little about the graph here. Look at this graph. Okay, this is the pressure inside the left ventricle. Look here, this is the pressure in the atrial pressure. Look, pressure in the atria is about 2 kilopascal. Therefore, when the both atria are contracting, it is a little pressure. But you can see how much pressure there is when the ventricle contracts. So this graph will show an increase in pressure in the wall of the ventricle. This is called tension, pressure. Okay, so you can see here only small pressure and in the atria when it contracts, and look at this pressure in the ventricle. It becomes 16 kilopascal. Okay, and this pressure, 16 kilopascal, is provided by the blood, by the heart, by the ventricle to the blood, and this pressure is maintained throughout the whole circuit in the artery. But when it comes in the vein, it is reduced. The pressure is reduced only in the artery. Okay. Now you can see here when atrioventricular valve close. Look at the valve here. Atrioventricular valve close. When it closes here, just before ventricular systole. Okay. So just before ventricular systole, atrioventricular valve close. But when the pressure, when blood is out of the ventricle, now don't forget that when the atrioventricular valve close, the semilunar valve open at the same time. You get that here it is time. At the same time, mostly at the same time, when the atrioventricular valve closes, the semilunar valve opens. So when this closes, this opens, so that blood do not move back into the ventricle, into the atria, and when this closes, contract and blood move into the pulmonary artery and the aorta. Now, you can see this, and here the opposite happen. Here the semilunar valve close and the AV open. So you should know all this. You should know how to label this in the examination. You will be told what is happening here. Or you will be told what is happening here, what is happening here, and what is happening here. These are the four questions that you will get in the examination. Here the AV valve closed, semilunar valve open. Here semilunar valve closed, AV valve open. Okay, you have to be used to this. Learn this by heart. Okay, now we finished with this one. This is a diagram to show the atrioventricular valve, and this is the semilunar valve. This is found here, semilunar valve, and this is found here, atrioventricular valve. Can you see here? There are muscles, small muscles, which called papillary muscles, which give tension to the tendons that hold the valve. If this tendon break, the valve will be harmed, and you have to to replace the valve. Unfortunately, many people, this tendon are broken. Okay, so and they have heart failure. Okay, they have to replace the valve. So these tendons prevent prevent the cup. It is a cup, right? Prevent it from inverting upside down. So it retains tension in the prevent it to open during the ventricular systole, because when there is a ventricular systole, there is big pressure inside the ventricle. So if the tension is not, if the valve is not well retained, it can move up the valve. You get the point? This is why we have all these tendons holding the valve. Okay, and here we don't have this tendon, because this is only a semilunar valve that prevent backflow of blood. In fact, all valves prevent backflow. This valve prevent backflow of blood, and this valve prevent backflow of blood in that direction, and this in that direction. So this is notes that I have written from your book, from your textbook. You just have to read it and to understand all what is taking place during the cardiac cycle. And if you have some suggestion or something that you can't understand, you just call me on this number. Okay, bye-bye.